Oh, okay. Welcome to the final session for today. Now we welcome Xiaofei, that is here. So, they say that it's better if you take this off. Click this here. Okay, he will give a presentation about his experiences in running a grid site.
Good afternoon, everybody. Now I start introduce my experience in running grid site. In our computer center, we not only manage our computer center, but also some other remote site. Because more institute and university join the LHC or HEPiX computing in China, and there are some small sites that are only physics and no computing expert. So they are lack of experience of grid computing and limited manpower to maintain the tier 2 or the tier 3 site. And another problem is network not good enough between the laboratory. In China, between this site, there is main two network. One is a science network, another is education network. Between this network is not good enough, the transfer bandwidth. And for the grid site deployment and configuration, and now there is no direct or simple way to finish the grid site deployment. Because there are many components and service to be configured. And in these years, there are many ways to deploy the WLCG site. First is manual, and then is YAM. And from 2009, we start to use Quarter to deploy our site. Now, then from the Quarter, we start the fully automatic installation and deployment. But in this year, during these years, and more the Puppet modules available, so we transfer to Puppet and Foreman deployment. We use Foreman to host provisioning and use Puppet to configuration management and patch error management, and use Git for the Puppet module version control. And this is our Foreman and Puppet deployment in our computing center. We use this distributed deployment, and one Foreman central server running Foreman dashboard and the HA proxy for the Puppet client redirection to the several of Puppet master, and the Foreman proxy to manage the DHCP and the TFT server and the Puppet. And we have a standalone Puppet CA to manage the Puppet authentication and two Puppet masters for the client request. And we have several Foreman proxy to running at some remote site to control the TFTP server and serve as a HTTP server for the OSD installation. This is a distributed Foreman server. Why we use distributed Foreman server? Because when in a remote site for the OSD installation, the OSD installation will fail when the TFTP transfer. It will take 1 or 2 hours to download the PXE image. Then it will fail. So I just install the TFT server in the remote site and controlled by the central Foreman server through the Foreman proxy. And add a local mirror. Then we can finish the remote site OS installation automatically. This picture is some remote site format proxy. And we use the load balance the Puppet master to finish, to optimize or to support more Puppet client. The Puppet client will make some request to the foreman server, and the foreman server, the HEPA proxy, will redirect the Puppet client to the server of Puppet master. So to finish this setup, we must set up the DNS or alt names for the Puppet master, and to create new certificate for the Puppet master with DNS alt names. We have made some optimization to support more client, and the Puppet modules, when the Puppet master serves, it will read some Puppet module located on the disk. So use the RAM disk. It's very fast for the Puppet module's read speed, and use SSD disk for the foreman database, and use RPM metadata package instead of Puppet package resource, because for each Puppet client we set up 1,000 of package to install on the client. If we didn't use the RPM meta package, it will take very long time for the Puppet master to compile the Puppet module, and for the Puppet client, it will take very long time to check the 1,000 of packages. If we use the meta package, it will just spend times in the first installation, and then it will don't need to check anymore. And then we optimize the HTTP parameters. And for the client, we set as play with 2. It will when the Puppet client start, it will when the Puppet boot, the Puppet client will start at the same time. If we boot 1,000 of time in the same time, the Puppet client will start in the same time. It will make 1,000 of requests to the Puppet master. So you can look here. Here, every 1 hour there is a peak in the Puppet master. When enable the S-play, the Puppet client will start random in 30 minutes. So the Puppet master load lower and smoothly than before. All the system is 6 times faster than before. From this picture, the client request is more faster, and the client apply time is more faster. The server response time is lower than before. And then we can decrease the client refresh interval from 1 hour or 30 minutes to 15 minutes. And for the Puppet module, for the grid site, there are a lot of EGI grid service now have a Puppet module to install. And these are some useful links to how to use the Puppet module to configure the grid site. And I developed some Puppet manifest to use these modules. You can from this link to look this Puppet manifest. This is one of the example to use the Puppet module to install DPM. First, from this link to there is a document how to use this module, and from this command, install the Puppet module. And then you can just create two files. One is for Puppet head node, and another is for DPM head node. Another is DPM disk node. After apply this Puppet client, the DPM can start online. This is the good service running in our site. And now we have two CEs. One is for Atlas CMS. We start support RCB in last year, so we set up a new CE just for RCB. And then because the cream CE will stop, so we will upgrade our CE to HT counter CE. The HT counter CE will serve the Atlas CMS and RCB. And we will change our storage element from two storage elements to only remain the DPM. This is we are testing the HT counter CE, and this we are aim to provide a unified CE and a batch system for all the tier 2s, and sharing all the resources in a uniform pool, matching resource by the accounting group. Now we are this developed with this popular module was developed from Ben John. So thanks Ben. So we are using these modules to test the HT counter CE. We will change all the configuration to our local, and we use our local Argue certificate batch system. We have some problem when testing this system. One is the authentication problem. Now this problem resolved, but we still stuck in some routine jobs to the batch system. This is one of troubleshooting we resolved. The issue is the NFS very high read and write rate and the IOPS is very high, and the IO weight is very high, so it caused a lot of job failure. The reason is the SATA disk have a very low performance, and the network bandwidth is only 1 gigabit. And the main reason is LCB job working space is running on the shared NFS. So we replaced from SATA disk to SSD disk and upgrade the network card to the 10 gigabit and change the LCB job working space to the local disk, and then this problem was solved. And we also attend some DOMA TPC test. We installed a DPM test node to join the DOMA TPC test, and there are some issues. First is the host certificate for the DPM node with no SAN FQDN in the host certificate, and we request a new certificate with FQAN SAN. Another problem is the Puppet cannot set the parameter for the Macaron, and then I used the Puppet Hera to set up this parameter. And in August this year, we used our production DPM to test the DOMA TPC. We upgrade our DPM to version to 1.13 and enable Puppet DOM and Grid FTP redirect. Now I'm publishing the JSON accounting information in the DPM. And for the grid running very well, we need some grid monitoring and accounting. There are some production links to know how the your grid site running, and some leaders is for the OPS, and all the site can look at this. For some in Atlas or the CMS experiment, you can look here. And we set up our local monitoring to monitor our local site and some remote site. This is the dashboard for our local monitoring. From here, we can look at some remote site. This is our local site. This is a part of our grid site monitoring. And we set up a new monitoring and accounting system. This integrate multiple monitoring data and analysis some various source monitoring data and unified display system. Provide some health data from multiple levels and show the trend of error and abnormality. This is some screencast of this new monitoring. This is our CPU resource usage. This is the grid site PBS status and job accounting. This is our HT counter accounting. After we upgrade our grid CE, cream CE to the HT counter CE, we can use this monitoring to accounting our grid job information. This is our file system monitoring, and we also have a security group to serve our computer center and some remote site to prevention, protection, and detection and response for the incident response. We set up a China Cybersecurity Federation for high energy physics. And this is cooperated to deal with security incident and share some threat information technology and expertise, and help our system admin and some remote site administrators with workshops and trainings, and communicate cooperation with HEPiX security teams outside of China. For instance, from CERN security group expert and from KK. And the security team also, they have give us a lot of good advice and very helpful for him. Thanks for him. This is the location of the members in China. We have a lot of institute and university to attend this federation. This is my presentation. Thank you.
Any question? No? So let's thank our speaker again. Now Domenico will give us an update on the benchmarking working group. Yeah, it's on. Can you hear me?
Doesn't seem so. Do you hear me?
Guys? Xiaofei, you broke it.
I can use the other. Okay. Hello? Yeah, it's fine now. I think they pushed the button. So, yeah, is the presentation done? That one. Okay. Yeah. Okay. So good afternoon, everybody. So I'm Domenico Giordano from CERN. I'm co-chairing the benchmarking working group together with Michele Michelotto and Manfred Aleph. So I will give this report on behalf of the benchmarking working group. Some members are in this room, and you will be able to discuss later. So many of you will probably remember what is the mandate of our working group is to define and maintain a consistent and reproducible CPU benchmark for WLCG. So this is the title, and in a given sense, so we are used to give status update every 6 months at the HEPiX workshop. But today I would like to cover this update in a quite different way, and this is also the reason why after my talk there will be another always on benchmarking from Chris. So what I want to cover are essentially 2 questions. Is HEPiX 6 still representative of the WLCG workloads, their performance on the CPU models on which we run and we will run in the future? And if not forever, what will be the benchmark that WLCG shall adopt after HEPiX 6? Also because probably you know that HEPiX 6 is based on Spec CPU 2006 that has been terminated in terms of support since 2018 because Spec CPU 2017 is out. Now, does it mean that we should move blindly or almost blindly to Spec CPU 2017, or shall we ask ourselves other kind of questions? So I'm sketching here a little bit the different kind of benchmarks that we were using in high energy physics in the past. So in the late 80s, there were a number. Among them, there was the CERN unit based on a mixture of simulation and reconstruction workloads from the experiments running in the 80s. Then we moved to SpecInt 2000. And then in 2009, we moved to HEPiX 6. And almost in that period of time, 2007, indeed, the HEPiX CPU Benchmarking Working Group was built, indeed, to evaluate the benchmark at that time and then move to Spec CPU 2006 and build the HEPiX 6. So now we are in a different era of software and benchmarks and computer architecture. So the experiments are evolving their software. They are moving to code that is multi-threaded or multi-process, is using multi-cores in different ways, are a different footprint, memory footprint respect to the past. So it's the right time to ask ourselves, so shall we just move to Spec CPU 2017, or shall we use something else? And this is what I will try to report in the next slides and convince you about the approach that we are following. So many of you will for sure remember what is the content of HEPiX 6. So it's listed there. Are 7 benchmarks. 4 of them are floating point dominated, others are integer point dominators. And here you can see the description of them. I'm sure that all of you remember that. But as you can see, so none of them is related to high energy physics. So the only thing that talks about simulation, something that is at the atomic level, is this multi-protein simulation. Then we have a numerical solution of partial differential equations, then solving a linear problem, ray tracing is not our tracking Kalman filter, okay? Is tracing for images. So simulation of a large Ethernet network, then 2D Pathfinder, and an XML parsing. Okay, this is what we have, what we currently run for accounting, procurement, performance tests. When a new machine appears, what we run is HEPiX 6 to get a feeling and say, okay, this will be better than others for our app workload, WLCG workload. Why we say that? Because in 2006, 7, and then 9, when we decided to move to HEPiX 6, it was done a study, a careful study, comparing Spec CPU 2006 with the workload of the experiment, and was found a very good correlation with the event throughput of generation, simulation, reconstruction that at that time on the CPU models that were available was studied. So reason why the team at that time selected the 7 C++ benchmarks, so what we call old CPP, and built around that with specific compiler flags on the rest, the HEPiX 6, okay? So, but then software is evolving, CPU models are evolving, and since 2015, we got feedback from the experiments that not all those workloads are scaling well with HEPiX 6. Here you see the first report at a GDB meeting from LHCb, from Philippe Charpentier, that was studying the performance of the LHCb jobs, studied for different CPU models as collected from the grid. And he was expecting to see for all the CPU models essentially a distribution that was picked at 1, but on the contrary, could see some of the new models picked at 1.5. when rescaled for HEPiX 6. The message was that essentially the performance of the job was order of 50% better than what HEPiX 6 was predicting. Good, so was not a huge concern because we were on the positive side. But in any case, this was a feedback that there are some workloads that do not scale anymore well as it was seen in 2007, 8, and 9. So reason why, in particular, we restarted the CPU benchmarking working group activity in terms of studies, also because some of our colleagues in the experiment were suggesting to use fast benchmarks, so the LHCb benchmark, the Atlas kit validation, the root stress test. So we dedicated a long time, I would say almost 1 year, to study in detail those fast benchmarks, and also to rule them out, to demonstrate that fast benchmarks cannot be used, are not reliable enough to use them in procurement procedure for accounting and the rest. They are good when one wants to have a quick feedback about the performance of a VM, in particular on cloud environments. We did also studies on the systematic studies on HEPiX 6 to understand the differences that we were seeing. So this magic boost that was seen by Philippe Charpentier, for instance. So we could absorb some of those correction factors due to the fact that HEPiX 6 still ran at 32-bit and the workload of the experiments ran at 64 bits. So 10 to 20% can be absorbed from that. At the same time, there was an expectation to move to SPEC CPU 2017, so to the next SPEC CPU that came out in 2017, and that we thought, okay, now this will solve our problem, we will adopt it. Indeed, was not the case, or at least is not the case, because we did a careful study studying the correlation of the score per core of HEPiX 6 respect to SPEC CPU 2017, studied on different CPU models, all available. Those are mainly all available models at CERN. So we range from Sandy Bridge to Hollowell, Broadwell. In the latest phases, we could also benchmark some of the AMD processors. And as you can see, there is a very high correlation. Okay, so this is when, for SPEC CPU 2017, we select also the C++ benchmarks. Why there is this very good correlation? The main reason is that, indeed, SPEC CPU 2017 is not very different respect to SPEC CPU 2006. Yes, they have made a little bit more complex the software. They are looking mainly to parallelize the system, to OpenMP. But what we have to use to mimic what is the approach of the experiments, the workload of the experiments, is something that essentially quite well overlaps with HEPiX 6. So 4 of the workloads are similar. Plus, there are others that are, let's say, different, but again, are in the same application area as HEPiX 6, and again, are not our application area. So we did more. So we wanted to really understand if there is a correlation due to the causality or not with HEPiX 6 and with SPEC CPU 2017. So we did studies taking app reference workloads and studying the performance counter, essentially using perf, and studying things like how much is used by an application in terms of access to the front end of the CPU, the back end, how many misbranch prediction, and so on and so forth. So that are plots like those ones where essentially the x-axis is the time, and here you have the percentage of usage for instance, a CMS DG workload. What we could see is that the experiments have a pattern of usage of the CPU. This is quite similar. I summarize this in a dendrogram of similarity, where when branches are not far apart means that they tend to be similar. When, on the contrary, there are huge branches that connect them, means that they are really dissimilar. So you can see that the HEP workloads tends to clusterize in a region of similarity. And here are all the spec CPU 2017 and spec CPU 2006 C++ benchmarks that tend to clusterize in another area. And they have their different behavior in any case. They are not so similar like we could consider the HEP workloads. Well, I have in the backup slides more details how we build this, but the main message is that we realize more and more that there is not causality in what we measure. So we had the idea, the proposal to the management board, and then we went to the GDB to start a project, an activity, a pilot in which we could build a suite based on high energy efficiency reference workloads. So we are somehow going back to what was the case in the late 80s. So the idea is sketched here. So today we have HEPiX 6 with the 7 benchmarks. And essentially, our workloads are in another application area respect to that. And we want to move to this condition in which the benchmarks come from our application area. And they will be nothing else than some of the workloads of the experiments that the experiment have selected based on the fact that they run those workloads on the grid. So we have for Alice the generation simulation, for Atlas generation, simulation, DG and reconstruction, for CMS generation simulation, DG and reconstruction, and for LCB gen and sim. Why they are also aggregated in different way? Because this is the way they run those workloads on the grid, okay? So Atlas does DG and Rico in the same job. CMS does gen and sim in the same job, but does DG and Rico in different jobs. So we can use the different workloads as a benchmark of that specific activity. So we started this project that involves a number of people. Most of them are from the experimental area, so they are the experts that can tell us how to run a workload. There are others that are mainly from the benchmarking working group that are doing development of a core infrastructure or testing. And everything is essentially publicly available in the GitLab repository and this Jira project that has all the tickets that we cover for the development and the testing phase. So we have structured this project essentially with 3 components, 3 pillars. One is the HEP workloads, then there is the HEP score, and then the HEP benchmark suite that I will detail in the next slides. But mainly the HEP workloads is what is able to run each individual workload of the experiment. The HEP score is what computed a single number that is the equivalent of a HEPiX 6 if you want. And the benchmarking suite is a meta suite that enables the possibility to collect data in a unified way, to compare results even with the HEPiX 6, HEPiX CPU 2017. So Chris will detail in the next talk all the aspects of the design and implementation, but here I want to sketch the main idea. So we are using containers. This is the technology that today we can use, we could not use 10 years ago, and makes this possible today. So the idea is to have standalone containers that have inside everything is needed to run a specific workload. We have to run a benchmark, so this is a limited sequence of events. That means that we can fix the input data, we can fix the condition data. The software itself is a subset of the full software. Typically, if we identify as configuration data as workload that we want to run, a very intensive one, like, I don't know, simulation of TT bar events, this is pretty representative of what will be the simulation TT bar events. So what we do is to put software, data, and or an orchestrator in the container. And then we run inside it. So the container has all the information that is needed to run, to spawn a number of threads that will saturate the CPU. We'll then look into the logs produced by the application of the experiment. In particular, we'll extract the throughput, the event throughput, so the number of events per second that have been processed, and we'll summarize them to produce a report in a JSON format. So to do that, there is a build infrastructure that is in place that is mainly based on GitLab as a testing phase or a distribution phase. We cover both Docker and Singularity as technologies, and we test both. Chris will detail this. In terms of readiness of the workloads that we have, as you can see from this table represents our test in terms of robustness, so the workload should not crash. The spread in the resolution, so the reproducibility of the results, the runtime, and the memory usage. And you can see it's almost everything green. Okay, that is good. It means that we are at good quality of those requirements. There are few cases in which we are still working, and there are already things that are ongoing and will fix, so are mainly known issues. So this one indeed should link to Alice. So okay. So the second component, as I was mentioning, so is the app score. This has the role of being able to be configured to run a sequence of workloads and then know from those workloads where the information is, this JSON report, and then compute a final score based on that JSON report, and then produce a report. Okay, so this is a sort of orchestrator of each individual workload. So the advantage of having this split with respect to the individual workloads is that we can configure app score and run any workload. If you tomorrow come with another container that has a workload from another experiment, from another domain, but that comply with the simple rules of what should produce as an output, we can embed this in the same procedure and extract the numbers and then evaluate the score due to this workload. So how the score is computed? Here there are a lot of similarities with the spec 06 and indeed with the spec CPU 2006 because there is nothing wrong in the way they do things. What we are questioning are the workloads that they run. So we have a number of workloads, so there are the different workloads of the experiment. Each of them is in a container. App score will trigger one after the other. Indeed, it will trigger each one 3 times so that we can do the median. So the workload, when we land in a server, in this case is a server with 4 cores, will spawn a number of processes or copies of the same process or threads based on the configuration of the workload so that it will saturate. So here we have, for instance, a container that starts 2 copies each of 2 threads. Here is another one that in the context starts a single copy of the process with 4 threads. Here, like LHCb and Alice, there is that are single threaded a single process, so there are 4 copies of the same process. They run. When they finish, we collect the throughput, the individual throughput of each copy, and then we sum up these. Now, this is still not the score, because this is the event throughput in that machine. What we need is a reference machine. So we will select, we are currently selecting one for testing, a reference machine where we have measured all the same scores. So we do the ratio of those scores. Why the ratio? Because with the ratio, so what I call here speed factor, we can compute the geometric mean. And the geometric mean, by definition of the geometric mean, will preserve the ratios. Means that if you have the geometric mean, so this app score of machine A respect to the reference machine and machine B respect to the reference machine, then you do the ratio of the two. It's like you were comparing the two and you forget the reference machine. The same way we use app spec 06. Now, the final component is the app benchmark suite. This is needed just because we realize that it's difficult to collect in a uniform way, a controlled way, the measurement done by several people in different data centers. So we typically get just a number, then we don't know exactly what was the configuration that this guy was running, and so on and so forth. So this suite is mainly, its purpose is mainly to be able to be configured to run a number of benchmarks, HEPiX 06, Spec CPU 2017, HEPscores, and others. So he has not inside those benchmarks, but is able to trigger them. So for instance, there are no problem of licenses because I have to install before in my machine HEPiX 06, and then using this suite, I can trigger HEPiX 06, it will run, it will produce its output, the benchmark suite knows how to parse the results, and then extract in a convenient way those results. The same holds for all the benchmarks, so that at the end, those fragment of reports plus the hardware metadata, so information about the data center, the CPU model, the kernel version, and so on and so forth, can be collected, and then a full report is built. This full report can stay on the machine, so available just for the person that is running, or can be published using essentially the Stomp client, and then publishing this to a transport layer. And here is a sketch of what, for instance, we are doing and we have done in the past. I'm using this extensively at CERN, so I'm benchmarking continuously machine at CERN in this way, but we have used it also for in commercial cloud procurement, so those is another cloud where we were benchmarking VMs, or in other sites that were using this same approach. So then those JSON documents, so the report of the measurement can be sent to a transport layer. We typically use an active NQ broker, and then can be consumed by several consumers. In particular, we collect those data in Logsdash that they land in Elasticsearch, and we can monitor through Kibana. We can then extract and do more analysis, like the correlation that we have seen between Spec CPU 2017 and HEPiX 06 was done in this way, collecting data in this way. Okay, so last point. This covers mainly the workloads as they are today, and I hope that I showed you that we are able to move also to the new workload as soon as they will appear. But the WLCG will move to heterogeneous resources, in particular because experiments are keen to move to heterogeneous resources. So we wanted to get also experience on that, in particular in the usage of GPUs. So we have investigated what are the workload of the experiments that already could run on GPUs. And among them, we have understood that most of them are mainly event reconstruction. They are boosted this activity by the online activity. And in particular, the one that is at the highest level of readiness is CMS, tracking reconstruction, with this project that is called Patatrack. So we have collected their software data, enough data to run on GPUs, and we have built a standalone container for that. So this will enable us in running this approach, this app workload also on CPUs plus GPUs, and understand how to benchmark a system like this. Okay, so many more details are in, linked to the agenda of the pre-GB of last week, that where we have covered all those these activities. So you are invited to go there if you want more details. And those are my conclusions. So I hope that I passed you the main message. So we have now this app benchmark chain full in place, so can be tested. There are people that already started to test, and it's useful for us to get feedback. There is work that needs to be done, that can be done in the next 6 months. In particular, we have to consolidate some of the workloads. We have to consolidate some of the procedure that we have for the HEPscore and the App Benchmark Suite. We have to compare Docker and Singularity scores. This is crucial. But we have already good feedback about the fact that what we produce when we use the right version of Docker, and it's reliable and confirms what the experiment measure typically on bare metal. So we are, I believe, on the right path. So finally, what we will do is to compare then the results that we are producing with the HEPscore respect to HEPiX 06 and the Spec CPU 2017. My expectation for the current situation is that they will be quite well correlated because there is still not a big discrepancy between them. But this will tell us that we are ready to move to something that is domain specific, so is HEP domain specific in terms of the workloads, but is generic in terms of the approach, also for other domains that could use the same approach. And that's all. So if you have a question now, thank you.
Okay. I am the first one with the
Yeah.
question. Does this suite also compile and run with different architectures? For example, ARM or Power or...
So we rely on Docker, so because, or Singularity, in the sense that we build the image that is self-contained there. So to run on ARM, as was mentioned this morning, so support, Linux support for ARM. So as long as on ARM we can have the same image running, that will be the way to go. We don't need to build that image.
Have you tried if the image runs?
There was an attempt a couple of years ago, and the guy that was doing this was able to run it, but then, okay, he went away and we did not continue. And this activity, in particular on ARM, is discontinued by the fact that there is interest that is coming and going away on ARM. So now there is more the hype on GPUs, so reason why we build the one on GPUs.
Okay. Other question?
Hello. I have a question. Do you have received the HS06 result or published the new result of HS06 in the benchmarks website?
You mean in the CPU benchmarking website, the HEPiX CPU? So typically this gets updated. There is a new procedure to publish the results on the new CPU models. So it needs to be submitted to a Git merge request and then included. But yes, and indeed Michele is going to update quickly this information. But this is, let's say, what I will call today the standard production way, okay? That is apart respect to what I have described up now. Okay, that is on the container.
I have been submit a result of the new CPU several years ago, but no, several months ago. It is not published on the website.
Okay, so please send an email to the mailing list and we will take care of that.
Okay, okay, thank you.
Thank you.
Other questions?
Thank you for the presentation. I just had a small question. I was wondering whether and how you randomize the layout. So for example, the memory layout or the size of environment variables or link order or stuff like that to get performance measurement across the various things that could change in real applications.
Yeah, so, well, I hope I will not spoil much of the Chris talk, but essentially, here, this orchestrator is the starter script that is the same that experiments a trigger to set up the environment through CVMFS. So inside the container, the application perceives the same environment as it is the one that the specific experiment is running on the grid. So it's nothing new respect to that. The novelty things is that we are able to snapshot just the part of the libraries that application is running for this short sequence of events, so that we can reduce the size of that image to a manageable one. So that what we could use as performance measurements, things like the CPU load, the memory access, and indeed having reference workload like this enable this kind of studies. All the CPU counters that I was showing before were based on that approach. What we want to use as a score is the event throughput, because this is what, on the contrary, for the experiment is important. Is really the figure of merit for the experiment, okay? At the end, what matters is how many events I can process or generate per second, and then per day, okay, on a given machine. And if you convert this to the cost of the machine, you have the event per money.
There was a question on the randomizing. I don't know if you're thinking about the random seed or the simulation.
Yeah, I just had heard that sometimes really funny things can affect performance in enormous degrees that I would never have expected. Like, I think the size of an environment variable, like your username, can affect the performance more than whether you compile with -02 or -03 in C. So I was just wondering, like, if the experiments like have really know that they stick to this environment, or when they change it, whether all of a sudden all results get.
So that is not the case for several reasons. First of all, what we have snapshotted is just one version of what is in CVMFS. There are just the libraries that we are using, and we reuse because you benchmark, so you repeat the same application. And then what is mentioned in Michele, so for this is for generation simulation. You have a sequence of events that you want to generate a simulator. So what we use is a fixed seed, so we fix the seed. This is true for most of the experiments. For some of them, now that they moved to multi-threaded, they cannot really determine the exact sequence. But so far, we have not seen things like what you were mentioning about changing the username. In any case, we use a single username, so we don't simulate that.
As I was expecting, the discussion is very interesting, but time
I think that Chris will generate a different discussion,
exactly.
so can be covered later.
Let's see Chris' presentation, and if we have time, we can discuss more on benchmarks. Okay. As already announced, it's Chris' turn, more on benchmarks.
Hi, can you hear me?
Again?
I think so, right? No? Hello? Hello?
I think they know.
Hello? All right, there we go. Okay, hi, so I'm Chris Hollowell from Brookhaven National Lab, and we just heard from Domenico about the HEP Workloads project, benchmarking project. I'm going to go into more of the design and the development details for this project. So, as Domenico mentioned, the HEPiX Benchmarking Working Group has started the process of creating a potential alternative for HEPspec 06 for various reasons. This is 10 years old. Spec CPU 2006 has been retired by the Spec Corporation, and various scaling issues that have been seen. And so instead of basing this on the all CPP benchmark components of our Spec CPU 2006, we're actually taking code from the LHC and putting it into containers and using that as the benchmark. So what's nice about that is, whereas before we basically did studies to obtain a correlation with the LHC experiments, performance software performance, now by using the actually HEP workloads, we're guaranteed to have the same exact performance. So the key feature here basically is encapsulation. We want basically to be able to package everything that the experiments need to run the software into a single thing. In this case, so we're using containers. And this makes it very nice because then you can basically run this anywhere. You don't necessarily even need network connectivity. So in order to run the container, there's several components that have to be included. So that includes the input events and conditions data, the operating system, and also a benchmark orchestrator. And what that does is basically just run multiple copies of the workload, and it has support for multi-threaded and multi-process workload applications. And it finally parses the output and generates a JSON file with the scores. So we are using GitLab basically for the project. And we're using CERN's, specifically GitLab. And you can see there's a link there if you want to take a look at what we've been doing. We've integrated numerous continuous integration tests into the project. So when people make modifications to the code, the containers are tested to make sure they're not failing, among other things. If the builds are successful of the containers, these are actually automatically pushed by the CI into GitLab has a functionality known as a registry, which is actually just a Docker registry that's built into it. And so the CI will push the production containers to that registry. So while these are built as Docker containers, we have tested they work with both Docker and Singularity, and there's just some examples of running the images on the command line here. You basically, when you run this, the my host path is where the JSON summary output file would be output. So one of the main ideas basically that we're using is CVMFS supports something called tracing. And when you enable this for a repository, basically every access to that repo is logged. So what this lets us do is basically determine, what we do is we start the initial build of the image, and we mount CVMFS as normal, and we run the application, and then we know exactly what it's using in CVMFS, and we then basically take the trace and pump it into CVMFS shrink wrap, which then extracts all the necessary components from the repositories and then includes them into the final image. And once that basically is tested via both Singularity and Docker and passes, it gets pushed into the GitLab registry. So one thing that's nice about this is that right now we're just using software from the LHC experiments, but pretty much anything that's software in CVMFS we could basically use and produce benchmark containers for workloads or other things, potentially things like RIC, SPhoenix. This also, because Singularity and Docker supports basically exposing GPUs to containers, this in theory could also be used to create GPU-based benchmarks. That's actually something that CMS is doing with the PataTrack project right now. Andrea Chabat is working on including that into a container. So Docker images are basically made out of layers, and we've made some optimizations to kind of improve the performance here. Basically, there are some layers that change quite a bit. There are some pieces of the software in the container that change quite a bit, and there are some pieces that don't. And we've tried to isolate these so that basically you can have some caching optimizations and that allow you to run builds and tests more quickly. And Singularity, even newer versions, actually support basically storing the Docker layers as well and caching these. So initially, the goal was to basically just use this with Docker, the HEP workloads. But given the popularity of Singularity, and it's basically designed to run scientific compute workloads, we performed various tests, and it was shown that this was functional these images were functional with Singularity as well. And as I mentioned, this has been formalized a bit more by including some CI tests in our continuous integration for the project. And basically, no changes to the images that break Singularity compatibility will be permitted to be merged into the code. So one thing we had, one of the reasons we really wanted to get this Singularity working is we had some users who wanted to test on SL6, and basically with newer versions of Docker, this is basically impossible. You can't run on SL6. Singularity, it is possible to run on SL6 with setuid, but you do need OverlayFS support to run these containers because of some missing directories. Unfortunately, OverlayFS is not available in SL6, so the solution to that was to use underlays, and this is a configuration option in Singularity that basically creates all the directories you need and bind mounts into there. This is something that, however, is only available in newer versions of Singularity or also in patched versions, older versions, for instance, in the packages that OSG supplies. So one thing that we also wanted to do was, this, even though we're using different code from different experiments, we really wanted to make the containers enforce as much commonality as possible in terms of the orchestration. So we actually have the base orchestrator script, which does base command line argument interpretation, spawning, parsing and production of the JSON results, and enforcing the JSON schema. And this is all done in a common script that basically the experiment-specific workloads source. And you can see, there's really not, to create the experiment-specific workloads, you can see on the side here, there's really not a lot of scripts to make it that you have to include for the experiment-specific components. So what is the output of the HEP workloads containers? Well, as I mentioned, it's JSON, and it includes the the total score up here, but also individual statistics are included, which are useful for some performance studies, including memory utilization, CPU utilization, things like that. Also, some of the workload metadata, for instance, the version of the container, the checksum are included, and this helps with validation. So if we want to create a benchmark suite, you basically need a tool that's going to orchestrate the sequential execution of the containers, collect the results, and then compute the final overall score. And we've implemented this in something we're calling HEPscore. And what were some of the features and requirements of this application? Well, we wanted to basically decouple the configuration of the benchmark from the actual application. So in order to make it future-proof, and also to allow other users to potentially, from other disciplines even, to use this, you write a custom configuration that specifies what workloads you want to run. We wanted to develop in Python. There's just, it's a very popular language, obviously. There's lots of modules available. And we wanted it to function with both Singularity and Docker. One thing we also wanted to do was attempt to minimize the third-party software requirements. So ideally, we really just wanted to allow this to be run on a system with stock CentOS 7 installed and Docker or Singularity, and that's it. And finally, we really wanted to have some traceability in the configuration and the output of this so that we could do validation studies. And the output, as I mentioned, it includes all of the actual all the JSON outputs from all of the sub-benchmarks as well, which helps from the validation standpoint. So what is the status? So right now we do have a beta application available for testing. Right now it's a single Python script. This is somewhat convenient because it simplifies downloading installation. You don't have to install an RPM or run any installation scripts. You can if you want to a pip install, but you could just download the script. And it has a built-in configuration inside of it right now, and this is for a very early prototype HEPscore 19 benchmark. This is, as Domenico mentioned, this is not finalized at all. This is just very early prototype, but it's convenient in that you don't have to pass a config. You just run the script, and by default, it will run this benchmark. As Domenico also mentioned, it's been fully integrated into the HEP benchmark project suite. And this really simplifies the performance comparison with other benchmarks like HEPspec 06. And because it's all searchable in Elasticsearch, all of the output is dumped there. So we also have various CI tests in place for HEPscore. So it's doing Python lint checking, bandit security checks, et cetera. And there's a link to the project in GitLab. And if you prefer to download the script directly, you can also do so using that URL there. So what does the configuration for HEPscore look like? So this is, I'll go into some more details later, but you have the benchmark name, the version, and you specify all the sub-benchmarks under the benchmarks parameter. And this supports various flags for the different containers. So you can specify debugging, the number of events, copies and threads if you wish to do so. You also can specify the Docker registry, which would make this usable with other projects besides HEP workloads. And it also allows for multiple repetitions of the same benchmark. And when this is done, the median is taken. And this is similar to the behavior that's been implemented in the HEPiX CPU 2006. And that is, we can do 3 runs of the same sub-benchmark. And what this does is it helps eliminate anomalous run data. So we do have one benchmark, Atlas Gen, for instance, which very rarely, from time to time, which for reasons we don't quite understand that are being investigated, will produce some kind of outlier score. And by taking the median, we eliminate that data, and the benchmark is still usable. Also, in the situation where, say, you had a cron job or something start up, it's using CPU on your system during a run, and that affects the score, that can be thrown out as well. So the method that's supported in the configuration right now, it's only geometric mean, and that's basically just the nth root of the product of the results. This is a fairly standard statistical method used to summarize unrelated data, and also, as Domenico mentioned, is what's being used in HEPiX 06. I think we want to add a weighted geometric mean function, however, in the future that would allow us to give particular weights to certain benchmarks. And that might be more useful for the final configuration for HEP score 19. The other thing that's been implemented is reference scores. So the idea basically there is you define a reference machine where you want the sub-benchmark score to become 1. So basically any results you get are divided by that reference score, and you now have units of the performance of that system. HEPiX CPU 2006 also does something similar. This is basically usually done, the reference machine you usually want to be something that's fairly old, but we're still working on exactly what it would be. I think for spec it's something like an ancient Spark CPU. There's also support for a scaling of the final overall score. So for instance, if we wanted to create a scaling factor to allow it to, the score to approximate HSO6 roughly, we would potentially be able to do so. So it just multiplies the final overall score by what you specify in that field. So how do we go about executing this? So you see up here just the example help output. The script does require PyYAML, but that is a standard part of the stock CentOS SL7 installation. You can also display the built-in configuration with the -p parameter. One thing I should note is that the HEP workloads containers do attempt to utilize all the logical cores by default, and you can't change this behavior in the command line. You can change it by modifying the configuration by specifying the number of copies and threads to utilize if you desire to do so. But if you really want to test only a subset of the performance of the machine, you're really better off probably offlining cores via sysfs. So if you want to run via Docker, you specify -d. -s is for running in Singularity. The output directory has to exist, and it will create a subdirectory that's date and time based under there, and share that as the results area with the containers that it runs, and also standard out and standard error or output to a log in that directory. So here's just an example run. So this is a simple one where we're just specifying one run of the Atlas KV benchmark, and you can see the configuration up here. So here's where I'm actually running it. I'm passing -s, so this is Singularity, -v for some verbosity, so I get all of the scores from all the runs reported. And the -y is specifying that I want YAML output instead of JSON. And you can see the final result is reported here. And you can see there's also some output YAML here and the output log data. So as I mentioned earlier, a prototype HEP score 19 benchmark is included as the default configuration of this utility. At the moment, it consists of 2 benchmarks from Atlas, 3 from CMS, and 1 from LHCb. We chose these as from previous studies. We've shown them to be very robust and reproducible. At the moment, the reference scores we're using in the config are based on a Haswell system. I think we probably want to find something a bit older because that will basically be the score, the one score. So it needs to be fairly old, I would say. The one issue is right now it takes something like 16 hours to complete. Again, the benchmarks are running 3 times. By comparison, the HEPspec 06 is about 5. Well, so we're studying, some ways to reduce the runtime. Perhaps we're reducing the number of events that are processed for each benchmark. And I think ideally we would at least want to include one benchmark for each LHC experiment, which we're not doing currently. And so basically additional discussion, work, and testing is needed to determine what the final benchmark set for HEPscore 19 will be. So in conclusion, the HEP Workloads project has developed benchmarks based on software from the LHC experiments. There's the GitLab repo there. And this was made possible through the use of containers and the CVMFS tracing mechanism. A beta version of the HEPscore benchmark utility is available for testing. The application includes a built-in configuration for HEPscore 19. We're still fine-tuning this, but we're hoping this will eventually become an alternative to HEPspec 06. And finally, HEPscore utility has been included into the HEP benchmark suite. That's all.
Thanks a lot, Chris. If there are any questions, also maybe a follow-up with Domenico presentation. We can include both. Edgar.
Thank you. You mentioned that you run the test in Singularity, but you don't mention, so where do you bring the Singularity images from? You have to download them in advance, or is there Python script downloads them from somewhere? Or?
So basically, Singularity can run Docker images natively. So basically, we're just passing the registry location to Singularity, and it runs the container directly that way.
Other questions?
Hi, thanks for the interesting talks. You mentioned in the earlier talk by Domenico that you are running the workload sequentially. Now, in reality, you may have jobs from different VOs running at the same time.
Exactly.
Does that have a significant impact? And also, if you don't start the jobs at the same time, because then instruction cache thrashing and stuff like that could maybe give you even some factors of performance difference.
So I think with benchmarking, you need to just eliminate variables. Maybe it isn't 100% representative of what's happening in the real world, but this is basically the best we can do without having those variables. I think Domenico probably would want to say something as well.
Yeah, I agree with you. But at the same time, a spec runs as we have described. So what we can do with this approach is also to mimic the grid behavior, because we can, and there are people in the working group working on that, to spawn with Kubernetes a number of those workloads, a mixture, okay, to see what is the effective performance when we have a more realistic case. But remember, for benchmarking, for procurement, we have to stick with a specific procedure, like it is for HEPspec 06.
And the other one.
Is it necessary to run this on an SSD, or is a normal hard disk sufficient?
You can run on a normal hard disk. I mean, most of the workloads are mainly doing CPU. I think we've been trying not to include much I/O. There is some that are doing I/O though. But yeah, we've been able to run on normal drives.
I have a quick question related to what Edgar said. If a new version of Singularity or Docker comes out and they promise to improve performances, what happens to our benchmarks?
So, I mean, as far as CPU performance goes, I don't think the container platform will change things very much. I think the only performance changes we'll get from the container platform are really from a disk probably perspective primarily.
The experiment will also then move to the new version when they will run jobs in Singularity or Docker. So we will evaluate what is this effect, like it was for HEPiX 6, shall we say to 32 bits or move to 64 bits, and then we can decide if it's worth for the benchmark to move to the new version of the container engine or not. But again, what will drive our decision is mainly the adoption of the experiments and the impact on the performance that we measure. Okay.
One thing I'll just add is what I've seen is the difference between Docker and Singularity performance, even though, so it's still ongoing studies, but what I've seen is it's very low. So on the order of a few percent. I think it's primarily due to I/O related, if I had to guess.
Yeah, I think we really need to be a bit careful here because, yes, we have a tool in hand now which is extremely flexible, and I am absolutely convinced that this will be a very useful tool not only to our community but to communities far beyond. So this is very good. On the other hand, we also need to keep in mind that despite all changes of the workloads that the experiments may apply, and all changes of Docker and Singularity and what have you, even if it only makes a few percent of a difference, this is something that of a reference benchmark you don't want, and you don't want to change a reference benchmark even every year or every 2 years. You want the reference benchmark to be stable for a longer time period. And just look at HEPiX 6. This has been a stable reference benchmark. Deviations of the real workload became ever more important for 12 years. So this is really what we should keep in mind. And this also puts a bit into perspective a remark you made earlier about the workload representing the real workload. At the point in time we fix the new benchmark as the reference benchmark, the workload is fixed. However, then the experiment workloads evolve. So you have basically exactly the same effect of a divergence of what the experiments really run on the farms to what your reference workload is. So this is
well, what's nice.
This we need to really keep into.
So we're versioning the containers, so we can basically hopefully create new future benchmarks more quickly to respond to changing experiment behavior, I guess.
Yes. On the other hand, is it really desirable to change more quickly? In terms of you base the accounting, you base the pledges, you base the requests by experiments, you base the procurement procedures on that reference benchmark. So I believe you would make a number of people very unhappy if you now decided, well, let's change the thing every 2 years, and then we always model the behavior of the experimental code very well, because there's many, many more aspects that get into this game. So we have to be very careful, and in that context, I would also like to encourage the working group to already plan a bit ahead in terms of what would be the steps to follow, even if the workload is not entirely clear yet, and you hope to include a workload for Alice. And you may actually talk to Dune and to Bell 2, whether it could be of use to these experiments as well, and so on and so forth. But in parallel, you could already think of what the steps would be to define a reference benchmark and get it accepted by the relevant bodies, and then establish it as the new reference benchmark, which is not an alternative. And I would actually like to question that line on your summary slide. It is not a potential alternative, it is actually a potential successor, which means that you need a transition scenario. And I can only encourage the working group to start thinking about this. What are the steps? Because this is a process which will also take quite a bit of effort and quite a bit of time.
Domenico? Someone wants to help me with the mics.
I will help. So I agree with you, the short thing. So, and let me comment why. Today, I don't think we should move to any other. So this is for a successor, as you mentioned. And the reason is that most of the workload experiments are still on the old fashion. So not all of them have moved in production, multi-threaded, using a HEPiX 512 and so on. So I will not use the workloads of today to fix the app score. I will wait for the new ones, so that then we can keep them for enough long time until when something will break again. Like for instance, they will move from CPUs to CPUs plus GPUs, but in a massive way. And then we have to take into account this. So what I want to pass as a message, the fact that there is more freedom now doesn't mean that we have to use all that freedom every year to change. But it's the freedom that enables us to fix something, but also to study different things, okay? So we have the freedom, but when we stick on a configuration, we will stay on that. And this will also move the discussion on other side and other communities, because we have to involve the accounting, the procurement, and all the rest. So we are trying to build a tool that will enable all those people to then choose what we want to use. And this has not been the case for HEPiX 6. It's fixed, so we cannot change anything.
Yeah, I guess when I mentioned, we could change it more frequently, I meant, so HEPiX 6 is 10 years, right? Hopefully, maybe more frequently than that, but not like every 6 months or every 2 months or something like this, so.
Yeah, I think we are very quick in adapting to new workload, so we can change it in, I think, in few months. Then it's up to the body that decide if the benchmark is still the good benchmark for our community. They must decide. So it's a political problem, not a technical problem. If they decide that the workload is not anymore representative, in a few months we can produce a new benchmark.
Maybe there is also the fact that if new CPU provide new instructions that all the CPU do not have, and the experiments are able to use it, having a new version with the support of this new instruction is useful for the new CPUs, but not for the old ones. And so being flexible could be a good idea. Sorry?
You can also create a big mess. In the same trend that Helge was asking, do you in the plan to invite other communities? Like once you fix some for the LHC experiments, are you planning to invite them, or are you planning to invite them early on so you have it all a bigger map of it? And I'm thinking of communities that use our same grid resources.
I mean, so I would certainly invite SPhoenix, being from Brookhaven, to participate in this. Perhaps Dune as well. Domenico may have other comments.
As long as they are based on CPMFS, for the rest, we can include also others. What is enough is that they comply with the report format, okay? Yeah, but the interest is exactly that.
Yes, so from my point of view, as a WLCG site, I'm fine with rolling a benchmark as long as I get a full pledge cycle before, so I can readjust my pledges to reflect the new benchmark. And if someday the benchmark runs half as fast, my pledges are cut in half. But I don't want to get this shift between pledge and accounting. That's my only concern. So for me, every 2 year, changing with a 1.5 to 2 year latency is fine, but then you probably don't want to change every year.
Other questions? No? So let's thank Chris again. And this is it for today. Now for the elite, we have the the board meeting. See you tomorrow.